All right. That's okay. All right. Okay. Redox reactions caused by electrical current called electrochemistry. So let's take a look at this. We'll get back to your other stuff in just a minute. All right. Galvanic cell. Device in which chemical energy is changed to electrical energy. All right. Uses a spontaneous redox reaction to produce a current that can be used to do work. Technically, could be the future of energy. I think it'll be probably more of solar, but if you can make an everlasting regenerating battery, you might be in line to make some money. Of course. All right, this is what a galvanic cell looks like. All right. And somebody explain to me the flow of electrons, please. Somebody explain to me the flow of electrons. All right, how many people say it again? So we all say it in chorus, so we hear it on the recording. Cathode. All right. All right. So very good. Why? Why?
It's going from the negative side to the positive side.
Aha. Aha. Negative to positive side. What would we label right here? What would we label that if we had a drawing? So what would it look like in Spencer's drawing? Uh-huh. All right, so let's see if we learned something earlier. So this would be 2 lines. Somebody pick for me a metal that this could be and a metal that this could be. And how would you know? We went over some points of emphasis just a little bit ago. Ooh, we're going to have to look at that standard reduction potential table. We're going to have to look at the standard reduction potential table. Then I have to look at the standard reduction potential table. Anybody? Bueller? 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 Don't fall in. Hello? Anybody have one? Which one? Okay. Anybody pick another one? To the right side. Ah, okay. All right. Very good. All right. So that would work. Zinc and copper. Very good. All right. Next. All right. Galvanic cell occurs at the oxidation occurs at the anode. Salt bridge. Reduction at the cathode. We have a salt bridge or porous disc. Allow a mix of ions to flow without extensive mixing of solutions. And a strong electrolyte is contained in the salt bridge. Can anybody give me some examples of a strong electrolyte? NO3, that's a good one. Potassium nitrate, that's a good one. Used most of the time. All right, potassium nitrate. Then we have a porous disc that contains tiny passages that allow hinder flow of ions. All right, so they're all not just moving and mixing the whole time. Okay, and here is a picture of a more intensified galvanic cell. So let's go ahead and break this down a little bit. All right. Does this remind you of anything you did for homework? All right, so we have half reaction. So this right here, half. All right, half reaction. The electrons are flowing from the anode to the cathode. All right, and inside here, we're instead of using porous discs, we have cotton plugs. I don't know why I keep saying dicks. Really don't know why. I don't know why. All right. So what do we have right here? What is this?
That's a solid zinc.
What is it?
Solid zinc.
Solid zinc. All right. What do we have over here? solid copper. All right, so now explain to me what's going to happen on top of the zinc or copper. What do you think is going to happen? Anything? Say it. This is going to gain mass. Gain mass. Lose mass. All right, so in this salt bridge, we have a strong electrolyte of KCl. And we have two solutions, a zinc sulfate and a copper sulfate solution. All right, so we're going to send, why would kind of, see how this is saying Cl is coming this way and K plus is going this way? Somebody explain to me why. Why do you think K plus is going to the copper 2 sulfate solution? Yep.
Because it's the cathode's positive, so it's the potassium.
Cathode is positive, so the potassium is going to go to the cathode. Ooh, all right. So electrons are going to cathode. So will positive ions. So will positive ions. All right, so that's going to go to the cathode, so will the positive ions. So Cl is going to go to the anode. Why? All right, so it's losing electrons. So positive ions will go that way. There you go. Negative ions will go that way because losing electrons. Okay, which means that this is becoming more positive. And needs negative ions to balance out. Oh, I'm doing the Michael. All right, so that's the whole concept of redox charge balance. When you're losing electrons, it says charge balance, and you're adding electrons to one side or the other. That's the deal, because one side's losing them, it's going to need those electrons, and you add them on that side. All right, that's the deal. All right, so zinc is oxidized to Zn2 plus at the anode. This is a half reaction. Why are the two electrons right there? What's happening? They're doing what with their electrons? Losing. And they're going over to the cathode. And who's gaining electrons? All right, what copper though? All right, the copper in the solution is gaining the electrons. And then it turns into solid copper. Okay, so just, a little clarification there if you missed that earlier. Well, I didn't go over it earlier, but now you know. Okay. Okay, so I have a little video here. Let's hopefully it works. Spontaneous redox reaction. Did I cut that out for you? Okay, anode oxidation, cathode reduction. Cat red cat, and anode, and then I got my Clifford.
Clifford! That was my shot. Wasn't there a shot?
A galvanic cell is a spontaneous electrochemical cell in which electricity is produced by means of a spontaneous redox reaction. In this
There you go.
A galvanic cell is a spontaneous electrochemical cell in which electricity is produced by means of a spontaneous redox reaction. In this cell, zinc metal will be oxidized and copper 2 plus ions will be reduced. To complete the electric circuit, the solutions must be connected by a conducting medium through which the cations and anions can move. This requirement is satisfied by a salt bridge, which in its simplest form is an inverted U-tube containing an inert electrolyte, such as sodium nitrate or potassium chloride, whose ions will not react with other ions in solution or with the electrodes. At the zinc electrode, zinc metal is oxidized, losing 2 electrons to produce zinc 2+ ions. At the copper electrode, copper 2+ ions are reduced, gaining 2 electrons to produce copper metal. Electrons flow from the zinc electrode to the copper electrode. The zinc electrode is dissolving the zinc 2+ ions over time, and copper metal is building up on the copper electrode. Click on one of the buttons to view that portion of the galvanic cell on a microscopic scale.
Okay, we'll do that. Thanks, Tom.
At the zinc electrode, zinc atoms are losing 2 electrons, forming zinc 2+ ions, which enter the solution. The 2 electrons lost by zinc metal flow through the wire to the copper electrode. Note that only zinc 2+ ions are shown in solution. Other ions and water molecules are not shown to focus on the oxidation of zinc metal to zinc 2+.
Okay.
The salt bridge contains sodium nitrate, which exists as sodium ions and nitrate ions in solution. As the zinc electrode is oxidized to zinc 2+, a positive charge builds in the solution due to the zinc 2+ ions. If this positive charge were not counterbalanced, the galvanic cell would cease to function in a short period of time. The negative nitrate ions flow into the solution containing the zinc electrode, and the positive zinc 2+ ions move in the opposite direction to balance the charge. For this cell, nitrate ions are chosen because they do not react with other ions in solution or with the electrode.
All right, charge balance. All right, look at the other
The
side.
salt bridge contains sodium nitrate, which exists as sodium ions and nitrate ions in solution. As copper ions in solution are reduced to copper metal, positive ions are removed and the negative charge builds up in the solution. If this negative charge were not counterbalanced, the galvanic cell would cease to function in a short period
So
of
some
time.
zinc are coming too.
The positive sodium and positive zinc 2+ ions flow into the solution
There's the
containing
zinc.
the copper electrode, and the negative nitrate ions move in the opposite direction to balance the charge. For this cell, sodium ions are chosen because they do not react with other ions in solution or with the electrode.
All right, nice little point there. And last but not least, the copper
Electrons
electrode.
formed at the zinc electrode travel to the copper electrode. 2 electrons combine with each copper 2+ ion in solution to produce copper metal. Note that only copper 2+ ions are shown in solution. Other ions and water molecules are not shown to focus on the reduction of copper 2+ to copper metal.
All right, good. Did you like the animation? Was it good? All right, thank you, thank you. All right, cell potential. All right, cell potential. A galvanic cell consists of an oxidizing agent in one compartment that pulls electrons through a wire from a reducing agent. In the other compartment, the polar driving force. Somebody mentioned this earlier. Sean, I think it was you. On the electrons is called the cell potential. All right, the E of the cell, or the electromotive force, EMF of the cell. All right, unit of electrical potential is the volt, and the unit that's all important, so you know what you're calculating at the end, is joule per coulomb. Okay, that is very neat to know. Like I said, chemistry, if you know the unit that you're calculating, then chemistry is very easy. If you don't know the units, then chemistry is very confusing. It's all about knowing the units. All about knowing the units. Okay. Next. Galvanic cell. All half reactions are given in that table. And I put it on the next page so you can look at the next page. Somebody talked about the standard conditions. When not. When a half reaction is reversed, same as anything else. Thermochem, anything that we've done this year, when we reverse reaction, what happens to the sign? It changes, it gets reversed. The sign is reversed. When a half reaction is multiplied by an integer, E remains the same. All right, that's something a little bit different. You don't change the electron, the potential of the cell. The galvanic cell runs spontaneously in the direction that gives a positive value for the cell. Okay? And then we have this wonderful handy dandy table, which you got last class. So let's take a look at this one right here. All right, let's see if you can do a half reaction. Let's see if you can do a half reaction. Try to fill in the two half reactions, and then we'll check it. You must look up on your standard reduction potential table for the actual values. All right, you can't just do it without the values. All right, so look up the values on your pivot.